In this part of the lecture, I'd like to discuss how finite difference formulas can be derived from Taylor series expansions and how we can use those Taylor series expansions to also say something about the error that we can expect to have in comparison to the analytical solution. Now, in the previous section, we already introduced quite some finite difference formulas, mainly the forward differences, backward differences, and central differences. And we actually came up with these formulas mainly from intuition. So the idea of approximating the tangent to a function by either taking a slope between a point and the point to the right of it, which is a forward difference, the point to the left of it, which is a backward difference, or points surrounding the current point that we're looking at, which is then a central difference. But some questions pop up when looking at these formulas. How can formulas like these be actually derived from a mathematical perspective rather than an intuitive angle? Why did the central difference approximation prove to be much more accurate than either the forward or the backward differences for the first derivative? And what can we actually say or do about higher order derivatives? So the second derivative or the third or any arbitrary order of derivative. Can we also derive some expressions in order to approximate those things? And that is what I want to try and convey to you within this section. So we want to come up with a general recipe for finite difference formulas. And the idea was already introduced earlier, but so the main point is that we want to approximate the derivative of f at a given specified point in its domain x sub I by using a weighted sum of function values of neighboring points. And so here you can see how this looks schematically. So we want to approximate the derivative here at x sub I, which corresponds to the slope of this purple line over here by using a weighted sum with these coefficients ai minus 2, ai minus 1, etc., such that we can approximate this slope, this derivative over here. Now there are obviously a lot of free variables here. So how many points do we use? So far we've only looked at schemes with 2 points, so a forward difference, a backward difference, a central difference. But obviously we can take more points. But how do we choose how many points do we actually use? And then also a question that pops up is how do we determine these coefficients such that the weighted sum actually is a good approximation to this derivative? And what can we say about accuracy? So how accurate is our approximation? Now, in order to answer all of these questions, actually, we will be using the concept of a Taylor series expansion. So we will be able to derive these coefficients, say something about the error, and also relate this error to the amount of points that we're using by making Taylor series expansions of all the function values for x which are not equal to xi. So for neighboring values of x, we should make a Taylor series expansion around x is equal to x sub I. And as we will see, this allows for a very natural way in order to come up with these coefficients, and let us say something about accuracy there. So before we dive into the great details here, let's take a brief look at Taylor series expansions. So Taylor series expansions are, well, they should be part of your calculus course. If you're not very familiar with them, I suggest you look into chapter 2, where they are discussed in a bit more detail than in the current video. But the main point of a Taylor series expansion is that for virtually all functions f under some mild conditions of differentiability and continuity, we can calculate the value of the function at any point x within its domain using only information at a arbitrary point x naught. So using only f and its derivative at x is equal to x naught. And the Taylor series expansion of such a function looks like this. So for any arbitrary x, we can write the function at x, so f of x, as the function evaluated at a different point, x naught, plus the difference in x times the derivative at x naught, plus these higher order terms. And if we just keep on including more and more terms up to infinity, we can completely recuperate the exact value of f at any point different from x0. And actually, this is really quite an interesting expansion, because this really allows, well, I still find this quite an astonishing expression. And I want you to share this this astonishment with me. So let's look at a example here. For example, let's take the function f of x is sine of x, and the sine of x, well, it's a function we all know, but in order to compute it, well, we're not very familiar with how to compute these things numerically. I mean, we know the geometrical meaning of a sine function, but if we plug in a value of x, say x naught is equal to 1 or is equal to 2, then computing this actually by hand is very, very non-trivial. And let's say here that we want to compute the function at any point x, and we just plug in as an x naught is equal to 0. So we want to compute the sine of x for any value of x using only information on f at x is equal to 0. So, well, we can do this by simply computing this series expansion for f of x is sine of x, and you can, well, I'm going to let you do this yourself, but you actually come up with this Taylor series expansion. So the derivative of sine becomes a cosine, and sine evaluated at 0 is 0, cosine evaluated at 0 is 1, and then you actually end up with this Taylor series expansion of an arbitrary function. When applied to a sine of x for x naught is equal to 0, you come up with this Taylor series expansion. And let's take a look at what this actually means. So here I make a plot of the function sine of x versus x. So this is a nice sine wave that we all know. And let's take a look at the right-hand side of this Taylor series expansion. So if we only look at the first term, so that is this first order term, x, we see that, well, this line, which represents the function f of x is x, is already quite close to sine of x for small x. But as we increase x, well, here the approximation of the sine function by only this first order term is very poor. But if we start adding more and more terms, we see that this series expansion on the right really will converge to the sine function that we have on the left. So adding this second term here, so that's a third order term, we see that our range of applicability of the series expansion of sine of x, this right-hand side, becomes quite a lot more valid. So even here, where our initial approximation using only the blue line was getting poor, we're getting better and better. And as we keep adding more and more terms, well, we see that we will basically, by adding an arbitrary amount of terms, we will be able to approximate the sine of x for any x that we choose. Also important here is that if we are close to our x naught, which is 0 in this case, then we can already get away with quite a limited amount of terms. So this blue line already is quite a good approximation as long as we don't pick our x to be too large. Now, in the previous slides, we discussed that this series expansion can be exact if we just take into account an infinite amount of terms. But obviously in a numerical setting, we cannot deal with infinities. We have to take a certain amount of terms in a Taylor series expansion, after which we will truncate the expansion. And that will lead to a remainder term. So let's say that instead of using this first expression, which holds an infinite amount, so this final ... indicates that there's an infinite amount of terms in the sum. Let's say that we truncate this after n terms. So we just copy here the first n terms, and then after that we truncate the expression. So we don't take into account any further terms of order higher than n. And in that case, well, this will not be equal, but this will be approximately equal. And in doing so, we kind of introduce a remainder term, which is the difference between the left-hand side of the top expression, so the difference between f of x and this finite Taylor series. And this will be a remainder term indicated by Rn here. And now Taylor's theorem gives us a expression for this remainder term. And this might seem very abstract at this point, but we will see that this comes in very handy when looking at errors in finite difference approximations of derivatives. It will all connect in the end, I promise you. So Taylor's term tells us that, well, this error that we're making, the remainder term, by not taking into account an infinite amount of terms in the Taylor series expansion, that this is proportional to the n+1th order derivative of f evaluated at some psi between x and x0. And well, you can already see if x is relatively close to x0, this term on top here will be relatively small. If n is quite large, moreover, if n is quite large, n+1 factorial will be very, very large. So this entire term will become very, very small. And if f is relatively well behaved, let's say, then the derivatives, higher and higher order derivatives of f, will tend to get smaller and smaller. And you can see that this is the case, for instance, for a polynomial function. But for almost all smooth functions, higher and higher order derivatives, well, they will not blow up. They will stay within certain bounds. So if your function is smooth, if x is close to x0, and if n is large, then this gives us very clear indication that this remainder term will be very small. Let's take a look at an example here. And in this example, well, we take a Taylor series expansion of a function, an arbitrary function f, which we want to evaluate at a point x1, and we take the Taylor series expansion around x0. We only take into account the first term and the second term, or the 0th order term and the first order term, and after that we will truncate. So this means that we would get rid of all these terms over here. And Taylor's theorem then tells us that, well, we can rewrite this remainder term as follows. This will be the difference in x squared over 2 multiplied with the second derivative of f with respect to xi for some xi in between x0 and x1. Now it might seem that this is somehow unrelated to what we've been doing before, but what we've been doing before in the context of approximating derivatives, but this will become clear in very short time. So let's take a look at a 2-point forward difference scheme for the first derivative, f prime of xi. We already looked into how such a forward difference scheme looks, but from an intuitive point of view. But now let's apply this Taylor series expansion strategy to the same kind of forward difference scheme, and let's see whether we can come up with the same end result and whether this also teaches us something about the accuracy of the method. So a 2-point forward difference scheme, this means that we will use point xi and point xi plus 1 in order to approximate the derivative at x is equal to xi. So we use a weighted sum of the function evaluated at these 2 points in order to approximate its derivative. So this will not be exactly equal, but we will see, well, we can then rewrite this into the following form, where this r is a remainder term or an error term. And at this point, it might seem unrelated, but we will see by the end of this slide, we will see that this r is very much related to the remainder term in the Taylor series expansion. Okay, so let's apply the strategy that we used or that I introduced in the beginning of this video, and that is in order to determine coefficients a0 and a1, well, what we need to do is we need to write a Taylor series expansion of f at xi plus 1 around the point xi. So if we do this, well, so we make a Taylor series expansion around xi, well, if you just plug in these things into this standard expression for a Taylor series expansion, we end up with the following. And I just use this shorthand notation that h is equal to the difference in x. So h is here, let's say, the spacing between the points in x. And we see that, well, we have this infinite amount of terms over here. So a 0th order term, so there is no derivative in here. A 1st order term, there is a derivative and h to the 1st power, a 2nd order term, etc. An infinite amount of terms. Let's group all these terms. So let's say that we would truncate actually after this term, and let's group all these terms into this following remainder term, which is based on Taylor's theorem from the previous slide. So we can rewrite this infinite amount of terms in this full Taylor series expansion over here by this single term where xi is somewhere in between xi and xi plus 1. So this is a powerful expression. This tells us that the error that we're making by only using these 2 first terms in order to approximate the function at xi plus 1, the error we're making is exactly equal to h squared over 2 times the 2nd derivative somewhere in between these 2 points. And well, if h is small, if h is small and f double prime is small, well, then this is small, and then this is a good approximation. Okay, now let's see what happens when we plug this expression back into the initial approximation expression, so into this initial ansatz for our 2-point forward difference scheme. So what we do is, well, a0 times f of xi plus a1 times f of xi plus 1. And we know that f of xi plus 1 can be rewritten in terms of function values at xi using this Taylor series expansion. So we just plug this guy in here, and then we end up with the following. Okay, so now let's see what we have here. So this looks like quite a long expression, but we can group some terms actually here. Now we have some freedom to choose a0 and a1 such that this thing on the left resembles the first derivative as much as possible, the first derivative of f at xi. And how do we do this? Well, we can do this by choosing that a1 times h is equal to 1, because then on the right hand side here we end up with f prime of xi, which is exactly the target that we're trying to approximate. So we want that a1 times h is equal to 1. Well, we can also choose a0 and a1 such that this guy, that this drops out to 0, because this is not something that we want. We don't want any contributions of f of xi here. We only want to approximate the first derivative, so f prime of xi. So we want to choose a0 and a1 such that this term drops out. Because this term, well, it can be quite large. Huh? If f of x and if f of xi is quite large, then this term will be quite large. We also said that if h is small and if f double prime is small, this term is quite small anyway. And actually, fortunately, because we now have two conditions on two parameters, so a0 and a1, we have two conditions here. So this final thing will be the error. We cannot cancel this out anymore using only two coefficients. So in summary, what did we do? Well, we tried to choose a0 and a1 such that we approximate the right value. So we want to approximate the first derivative of f such that we cancel out the lower order terms, and then we end up with this remainder term, which then will be what we call the truncation error. And we cannot cancel these out anymore because we have only 2 degrees of freedom here. So looking at these two conditions, well, we have that a0 plus a1 will be equal to 0. And we have that a1 times h will be equal to 1. So this is this will end up as a linear system, 2 equations, 2 unknowns, and you can easily solve this. And the outcome will be that a0 is equal to minus 1 over h, a1 is 1 over h. So plugging in these values for a0 and a1 into this original expression, we end up with the following. And we find that the derivative is equal to this finite difference expression plus the r term that we also found in the previous slide, and this r term can be expressed as follows. So what we see here in this formula is, well, we have a finite difference approximation, and we see that this is completely similar to the forward difference approximation that we derived intuitively in the previous section. But also we now have a expression for the truncation error that we're making. So that is the error that we're making by not including more and more terms in this Taylor series expansion. Interestingly is that, well, this xi, even though we are guaranteed that there exists a xi in between xi and xi plus 1, we do not know what this xi actually is. However, we can say, well, at least in this figure, this function f is quite smooth. So the first derivative will be smooth, the second derivative will be smooth, and it will also not be extremely large from a qualitative point of view, at least here. But interestingly, so we know that this thing will be not infinite. It might be it might not be close to 0, but it's not infinite, so that's nice, because we know that this truncation error will go down with h. So if we choose h smaller and smaller and smaller, this formula indicates that the truncation error will get smaller and smaller and smaller as well, and exactly proportional with h. And that is actually something that we observed also in the numerical experiment from the previous section. So that is what we see here. And this is what we call first order accuracy, because the truncation error goes down in the same way as h goes down. So it is proportional to h, and that is somewhat equivalent to this notation here, which means that we say that it is of order h. So by making h go to 0, we make the truncation error also go to 0 at roughly the same rate as h goes to 0. Let's take a look at another scheme, a central difference scheme. In central differences, well, we choose here 3 points. So we choose the point itself, we choose the point 1 to the right, and a point 1 to the left. And again, the goal is to approximate this derivative of f at point x is equal to xi. Again, we follow simply the same routine that we did in the previous case. So we make Taylor series approximations around xi, and here we write it out up until the third order term. And you can verify these things by hand if you want. So it's completely analogous to the previous case, where we just now have to make Taylor series approximations for this guy and for this guy. And then we can simply plug these things back into the original expression, and we end up with the following. So here we see that this right-hand side of the formula, by plugging in these Taylor series expansions in there, we find that we obtain the following. And here we have three coefficients that can be chosen from. And again, we will choose those coefficients based on certain conditions that we want to meet. The first condition that we want to meet is that we want that this term is simply equal to the derivative of f. We see that here this term holds the derivative of f at xi. So we basically want to say that minus a minus 1 plus a1 times h is equal to 1. Let's take a look at the other terms that we have in here. This first term on the left over here. So f of xi, well, that is in the general case, that's non-zero. So this can be regarded as an error that we want to get rid of. How do we do this? Well, simply by making it 0. So we can choose these coefficients a minus 1, a0, and a1 such that this term over here on the left is equal to 0. We can also do the same for this guy over here. So this is then something times the second derivative. Well, we don't want anything to do with the second derivative. In this approximation, we're looking for something which is close to the first derivative. So we also want to cancel out those terms. And this will come down to saying, well, we want a minus 1 plus a1 times h squared to be equal to 0. Again, this will lead us to three conditions, 1, 2, 3. We have three unknowns. So this final term here on the right, that is something we cannot really change. That is something we can't do anything about. That will be the truncation error that we have to live with in this case. Note that this thing is proportional to h cubed. And since we tend to take h small, this error term will definitely be relatively small. At least it will be smaller than this term over here. So here we have an h squared, and if h is small, h cubed is much smaller than h squared. So we should first aim at these lower order terms in order to cancel those guys out, and then proceed to higher and higher order terms. And that's the entire strategy. So here we end up with three equations again. So we have this condition, which leads to the equation a minus 1 plus a0 plus a1 is equal to 0. We have here that minus a1 minus 1 plus a1 times h is equal to 1, which translates to this one. And here we simply have that a minus 1 plus a1 is equal to 0. This is, again, a linear system, three unknowns, three equations. H is known, and h is a predefined input. That's the grid spacing that we have there. So we simply solve this, and what comes out is these three coefficients. So plugging it all back in, well, we recover something we already saw before. So we see here clearly that we have this finite difference approximation for this corresponds to the central scheme that we also saw in the previous section. So this looks like a 2-point scheme, but that's simply because this coefficient, which corresponded to the center point, so this a0, is actually equal to 0, and that's something we were able to prove mathematically using these Taylor series expansions. And also we find here the truncation error, which is h squared over 12 times, well, here we have then 2 of these xi1 and xi2. And we know that, well, we don't know xi1 and xi2, but we know that xi1 is somewhere in between in this interval, and we know that xi2 is somewhere in this interval, so between xi and xi plus 1. And it's important, again, to stress that we don't know the actual constants here that show up, so we don't know these multiplicative factors that go into there, but we know that the truncation error is proportional to h squared. And that's very important because h squared, as we make h smaller and smaller, h squared will go to 0 anyhow. And it will go to 0 smaller, so h squared goes to 0 faster than h. So this means that this truncation error will go to 0 quite fast. And this is what we call second order behavior. And this is also what we actually what we observed in one of the previous examples, where we saw that the central approximation, it was much more accurate than the forward approximation of the derivative. So if you recall from the previous section where we did a refinement where instead of h is equal to 1, we chose h is equal to 0.25. So we reduced h by a factor of 4. And we saw that for the forward scheme, the error went down with a factor 4 also, which is first order behavior. So the truncation error is completely proportional to h. We saw that for the central scheme, the error went down with a factor h squared, or a factor of 16. So that is second order behavior, which is very, very beneficial from accuracy point of view. Now you can keep on applying this strategy in order to go to much more accurate and higher order schemes. So if you start adding more and more points in your approximation of the derivative, this will allow you to cancel out not only the very low order terms, the low order error terms, but also the higher order error terms. And in this sense, you will obtain a truncation error, which is maybe proportional to h to the power 4 or h to the power 8. And that means that your truncation error goes down extremely fast as you decrease h. So adding more points allows you to cancel more terms, and this greatly reduces the truncation error and significantly increases the accuracy. Now, I'm not going to do this in this lecture here, but I would suggest that you try out yourself to derive the 5-point central difference scheme for the first order derivative. So you need to find the coefficients. So the 5-point central scheme, well, that will involve point I minus 1, I minus 1, I minus 2, I minus 1, I plus 1, and I plus 2. So 5 points centrally around xi. So you need to identify 5 coefficients, the one corresponding to this point, the one corresponding to this point, etc. So those will be 5 coefficients that you're able to determine, and you should try to find the truncation error and the order of accuracy. So I'm just going to give you the end result now, but I strongly suggest that you try to derive this scheme yourself. So what you would find in the end is that the coefficients would be 1 over 12h, minus 8 over 12h, etc., and that the truncation error is of order h to the power 4. So this would be a fourth order accurate approximation of the first derivative. A question that has remained unanswered so far is, how do we, instead of approximating the first order derivative, how do we approximate higher order derivatives? So for example, what do we do when we want to approximate the second order derivative f double prime at a point xi within its domain? And the answer is actually, in order to derive such a scheme, such a finite difference scheme, there is very little difference in what we need to do when deriving second order derivatives or first order derivative approximations. But the only difference is that the error terms, that we want to cancel or the target terms that we want to make equal to 1, that they actually differ depending on what kind of value that we're trying to approximate. So let's take a look at an approximation for the second order derivative using a central difference scheme. So here we have the second derivative at xi, and it's a central scheme. So we use xi minus 1, xi, and xi plus 1. And similarly to when we did the same thing for the first order derivative, well, we just start by writing out Taylor expansions for xi minus 1 and f at xi plus 1. So this is familiar from the previous slides. And we then plug those things back into the original expression here. And this leads to the following. So if we take this this expression on the right, we multiply a minus 1 with this Taylor expansion of f at xi minus 1, etc. We come up with the following. And this is completely the same formula as we've seen 2 slides ago. With one key difference here is that we do not want to approximate f prime in this case. No, we want to approximate f double prime. So this means that our goal here is such that this term will in the end be equal to f double prime at xi. So we can choose a minus 1 and a1 such that this evaluates to 1. And the other terms are the error terms. So that are things that we do not want to approximate. Those are things that we, as much as possible, want to get rid of. And we start with the lower order error terms. So this one, well, again, simply choose a minus 1, a0, and a1 such that this vanishes, goes to 0. We choose a minus 1 and a1 such that this first order term goes to 0. And now we have 3 conditions with 3 free variables. So a minus 1, a0, and a1. So there's not much more that we can do. This is the truncation error that we'll have to live with. So again, we would be able to write 3 equations in 3 unknowns, and you can do this again by yourself, but I will just give you the final answer. The coefficients that you will come up with in the end will be 1 over h squared minus 2 over h squared and 1 over h squared, such that you have this central finite difference approximation of the second order derivative. And we see also that the truncation error that you will come up with is of second order. So summarizing, because this might have been quite a lot to handle, but I think this is really quite important to be able to derive these finite difference schemes from Taylor expansions. So our goal in the beginning was to come up with a general strategy with which we can derive these finite difference schemes in order to approximate derivatives using neighboring points. So that's the entire idea of finite difference schemes, is using a weighted sum of function values evaluated at points neighboring the point where we want to evaluate the derivative actually. We saw that using Taylor expansions, we're able to determine these coefficients, so the weights in our weighted sum, and that this allows us to kind of make our approximation as accurately as possible and gives us an estimate for the truncation error, also such that we are able to kind of distinguish how fast this error goes down if we make h smaller and smaller. We saw that adding more points allows us to attain higher accuracy. So we've seen a forward finite difference scheme, which was first order accurate, a central finite difference scheme, which basically actually uses 3 points, which is second order accurate. I didn't do the derivation in full on the slide, but I showed that a 5-point scheme allows you to attain fourth order accuracy, etc. And you can keep adding more and more points if you want in order to attain a higher order accuracy or a better approximation of the derivative. And finally, in the final slides, we discussed how this Taylor series expansion strategy also simply generalizes in a very natural way in order to come up with finite difference formulas for higher order derivatives. And we did this for the second order derivative, but you can just as easily come up with finite difference schemes for third order derivative, fourth order derivative, using forward schemes, backward schemes, central schemes. And you can easily see that, well, in the end, this will lead to a big collection or an entire zoo, so to speak, of finite difference formulas. And in the next section of the handbook, there is a summary provided of many of these schemes, and I will stress the most important ones in the next lecture.